Hello students, in previous lecture we have talked about the convergent sequences, divergent sequences, types of divergent sequences, sequence diverging to infinity, minus infinity and oscillatory sequences. We have also proved that if given sequence is convergent then it has unique limit. Today we will prove some results about convergent sequences. So we will see first result that every convergent sequence is bounded. Then we will prove that subsequence of convergent sequence is convergent and it converges to limit of the original convergent sequence. So what is our theorem? Theorem number 2. Every convergent sequence is bounded. As we are studying real sequence, means every convergent sequence of real numbers is bounded. In fact, in any metric space also, every convergent sequence is bounded. So let Sn n is equal to 1 to infinity be convergent sequence. Once it is convergent sequence, it has some limit. Suppose limit of Sn is equal to L. Limit Sn is equal to L. Therefore, for given epsilon greater than 0, there is some positive integer n such that mod of Sn minus L less than epsilon for every n greater equal that particular integer n naught. So, if as boundedness, we will choose that epsilon to be 1. Then, for epsilon is equal to 1 greater than 0, there exists positive integer n naught such that mod of Sn minus L is less than 1 for every n greater equal n naught. 1. Now, mod of Sn. I have to show that Sn is bounded, means Sn lies between two fixed real numbers. If mod Sn is less than m for fixed positive real number m, then minus m is less equal Sn less equal m. We will get that lower bound and upper bound. So I am taking mod Sn and we will relate this mod Sn via limit of the sequence. As convergent is given, so it has some limit. So mod Sn is written as mod Sn minus L plus L. Then by using the triangle inequality mod A plus B less equal mod of A plus mod B, this is less equal mod Sn minus L plus mod of L. Then by 1, this is less than 1 plus mod L for every n greater equal n naught. So after n greater equal n naught, all Sn's have modulus value less equal 1 plus mod L. Before n naught, we have only now S1 term, S2 term, dot dot up to Sn naught minus 1. I have to also give some bound for them. So, and for n greater equal n naught, all Sn's have modulus value is equal this. So, take m is equal to maximum of mod S1, mod S2 and so on, mod of Sn naught minus 1, or if you take Sn naught also, okay, and 1 plus mod L. Then mod of Sn must be less equal m for every n greater equal n naught from 2. Because after n greater, for all n. After n greater equal n naught, all mod Sn's are less equal 1 plus mod L, and due to the choice of m, mod Sn must be less equal m for these values, and this is positive real number. This implies Sn is bounded sequence. Here we proved every convergent sequence is bounded. If we are proving some results if then type and its converse part is not given, whether it is true or not, if it is true, then there will be that converse part the result. If it is difficult for proof at your level, then they will say that proof is beyond the scope. As it is not mentioned in book, so converse must not be true. If for if then statement converse is not true, then always construct at least one simple example to show that converse is not true. So here we have to construct some simplest possible example of bounded sequence which is not convergent. So in previous lecture I explained that minus 1 raised to n equal to 1 to infinity is the divergent sequence, is oscillatory sequence. It has no limit, but it has term minus 1, 1, minus 1, minus 1 and so on. Mod Sn is equal to 1. Okay, so means that sequence is bounded. Okay, so note minus 1 raised to n is bounded sequence but not convergent. Okay, so this is the example for converse is not true, simplest possible example. Okay, now our next theorem, if given sequence is convergent, then we will talk about what will be the limits of their subsequences. So we'll prove that any subsequence of convergent sequence is also convergent and converges to same limit. Okay, so any subsequence of convergent sequence is convergent and converges to limit of sequence. Proof. Let Sn be convergent real sequence. Be convergent sequence. Suppose limit of Sn, it has some limit. Limit of Sn is equal to L. We'll give 1 for it. Let Snk k equal to 1 to infinity be subsequence of Sn. What is our aim? Snk is convergent and converges to limit of original sequence. What is your claim? Limit Snk k tends to infinity must be L. Okay. So from 1, for given epsilon greater than 0, there exists positive integer n naught such that mod of Sn minus L is less than epsilon for any n greater equal n naught. This implies mod of Snk minus L is also less than epsilon if that nks are greater equal n naught. n1, n2, n3s are greater than n naught. Then mod Snk minus L is also less than epsilon because that nks are contributed in this original sequence Sn also. This implies limit k tends to infinity of Snk is equal to L. Means for given epsilon greater than 0, same n naught works here. And therefore, Snk is convergent and converges to L. Hence proof. Hence result is proved. What is use of this result? If you have to show that some sequence is divergent. By using negation of convergent sequence to prove given sequence is divergent, it is a difficult one. Now, what is negation of this statement? If the given sequence has some subsequence which is not convergent, then original sequence must not be convergent. And if we are able to find two subsequences which converge to different limits, then original sequence must not be convergent by using this theorem. And that negation is important for us. Okay, so example, so that say 1 2 3 1 2 3 and so on. This is my SN sequence. It's divergent. It is oscillatory sequence. It doesn't goes to infinity. It doesn't goes to minus infinity also. So it is oscillatory. Okay, a divergent and oscillatory. Okay. So solution for this sequence, if I take S3n, what is S3, S6, n equal to 1 to infinity, this sequence will become 3 3 3, which is constant sequence, and constant sequence always converges to that term of that sequence which tends to 3 as n tends to infinity. And if I take S2n, it will become 2 2 2 and so on. It tends to 2 as n tends to infinity. Therefore, Sn has subsequences converging to different limits. And therefore, by this result, given sequence cannot be convergent. Therefore, Sn is divergent. Okay. Now, why it is oscillatory? As Sn doesn't goes to infinity, clearly Sn doesn't goes to infinity. Okay. So, moreover, 1 less equal Sn less equal 3 for all n, and therefore Sn is bounded. So Sn is bounded divergent sequence. Sn is bounded divergent sequence. Any bounded divergent sequence is always oscillatory sequence. Therefore, Sn is oscillatory. It cannot go to plus infinity or it cannot go to minus infinity. There exists unbounded sequence which is also oscillatory. So what is the example of unbounded sequence? Unbounded oscillatory sequence. So if I take sequence 1 2, if I take 1 minus 2 3 minus 4, then 5 minus 6 and so on. So for this, you can observe the odd places takes 1 3 5 and so on. That approaches towards minus infinity. Even places takes negative minus 2 minus 4 minus 6 and so on. That approaches towards minus infinity. Therefore, Sn must not be bounded sequence. And it has subsequence Sn. Say S2n minus 1. which diverges to infinity. So given sequence has subsequence which is not convergent, therefore this sequence must be divergent. This sequence must be divergent and it is oscillatory. It cannot go to plus infinity, it can't go to minus infinity. So it proved any subsequence of convergent sequence is convergent and it converges to same limit. 1, 2, 3, 1, 2, 3, if I had to show that it is divergent by using epsilon n definition for convergent sequence, it is somehow difficult task, not too difficult, but somehow difficult. So if you use such type of result to check the convergent divergence of the sequence, that is useful. So now we'll also observe that if given sequence has all terms which are positive, then its limit cannot become negative. Or if all terms of convergent sequence are negative, then its limit must be negative. So we'll try to prove this result. Okay. So what is our next theorem? Here, if Sn n is equal to 1 to infinity is convergent sequence of positive real numbers such that limit of Sn is equal to L, then L must be greater or equal to 0. L must be greater or equal to 0. Here, even though we are proving result for sequence of positive numbers, then limit of Sn is that one. Okay. So proof. Since limit of Sn are given, limit of Sn is equal to L and Sn's are greater than 0 for all n. If I take non-negative real numbers, claim L greater or equal 0. On contrary, suppose L is negative. Okay. On contrary, suppose L is less than 0. Then, on contrary, suppose L less than 0. Then, for epsilon is equal to minus L by 2 greater than 0. If L is negative, then minus L by 2 is positive. There exists positive integer n naught such that mod of Sn minus L is less than minus L by 2 for any n greater or equal n naught. Therefore, L minus L by 2 is less than Sn is less than L plus minus L by 2 for any n greater or equal n naught. Now, if I only compare this part here, we get Sn is less than L minus L by 2, Sn less than L by 2, but L is a negative number, therefore Sn less than L by 2 must be less than 0 since L is less than 0 for every n greater or equal n naught. This is contradiction to hypothesis. What is hypothesis? All to hypothesis Sn greater or equal 0 for all n. Therefore, our assumption is wrong. Therefore, our assumption is wrong. And therefore, L must be greater or equal 0. Hence, the result is proved. Hence, proved. On same line, if Sn is a convergent sequence of non-positive real numbers, means 0 or negative real numbers, and Sn converges to L, then L must be less equal 0. In that case, if L is less than 0, L less equal 0, then minus L by 2 is positive number. Minus L by 2 is positive number. And on same line, we'll get contradiction. In that case, here you have to compare left side inequality to get the contradiction. Okay. Even though here we are assuming that Sn is convergent sequence of non-negative real numbers, but we know that if the limit of sequence exists, then we are observing that Sns are very close to L as n tending to infinity. Means up to finite number of terms, even though there is a variation, positive, negative terms. After 1 lakh terms, suppose all Sn maintain this condition. Sns are non-negative real numbers after n greater or equal to 1 lakh. And limit of Sn is L, then L must be greater or equal to 0. So that finite number of terms doesn't affect on the result. While proving the result here, while choosing positive integer n naught, I'll take n greater or equal to n naught greater or equal that 1 lakh also. And we'll get the required result. That is also important part. I have explained for non-negative real numbers, non-positive real numbers. On same line, if I have convergent sequence Sn, n equal to 1 to infinity, which converges to L, and if all terms of that sequence Sn lies between two numbers L and M, L less equal, Sn less equal M, then limit of Sn must lie between that two numbers L and M. L and M. Easily we can prove that result. So with this discussion, we'll stop here. Bye bye.